Hi there, my name is Jesse Bristow, and I'm going to be presenting my research project, Teaching a Machine to Draw Using Reinforcement Learning. My supervisors were Dr. Stephen James and Professor Benjamin Rossman. Drawing and art have always been a big part of human culture throughout history. We have used drawings and paintings for things like communication, art, and historical records. The current state-of-the-art machine learning algorithms or techniques are now sophisticated enough to be able to teach computers to draw. This can be beneficial for many reasons. For example, it can help with education, it can assist artists in creating virtual artworks, or it can even be used to create art that can then be sold. We present a method whereby we use a reinforcement learning model in order to recreate a given input sketch image using a list of sequential drawing actions. A drawing action consists of drawing a line from the model's pen location to some other pixel on a simulated drawing canvas. The specific reinforcement learning algorithm we use is known as a deep Q network or DQN. There have been many previous attempts to generate art or drawings using machines. Some of these methods included manual engineering algorithms. These kind of algorithms are algorithms that don't really require any prior learning. There have also been methods such as the use of generative adversarial networks or the use of supervised learning techniques. There have also been previous reinforcement learning approaches which vary in implementation. Some of these require supervised learning to learn initially, though. We present a novel reinforcement learning approach to recreate a given input sketch using sequential drawing actions and a deep Q network without the need for any supervised learning. For our methodology, first we needed to create a simulated drawing environment in order to allow the agent to draw and learn. We represented our state, which is essentially the information the agent has in order to make a decision. We represent our state as a combination of two cropped image patches and two values representing how much of the drawing the agent has completed. The two cropped image patches are generated by cropping both the canvas image and the input image such that these cropped images are centered around the agent's pen location. We then defined our action space such that each action consisted of drawing a line from the agent's pen location to some pixel in the cropped image patch surrounding the pen's location. We then rewarded our agent for drawing pixels correctly, penalized it for drawing pixels incorrectly, and also experimented with penalizing it for drawing over previously drawn pixels. The model architecture we use for our DQN algorithm is a convolutional neural network with some fully connected layers. Lastly, we implemented the DQN reinforcement learning algorithm in order to control the actual learning. In order to optimize our model to perform well, we needed to make a few crucial design decisions. In order to make educated decisions, we performed several experiments. In the end, these experiments allowed us to develop a competent final model. We experimented with the use of a convolutional neural network for our network architecture compared to the use of a neural network. We also experimented with the use of different sized cropped image patches. And lastly, we experimented with different reward functions. Finally, to convey the performance of our model, we trained it on numerous different test images to see how well the model recreates them. Now to show some results. These are three images that the model tried to recreate. We see the first image is essentially the input image. The second image is the final canvas image that the model produced. Then the first graph refers to the average rewards achieved by the agent per episode during training. And the second graph kind of measures the metrics of performance per episode over training. More specifically, it measures how many correctly drawn pixels there were on average, number of incorrectly drawn pixels on average, and number of times the agent backtracked over previously drawn pixels on average per episode during training. Now, I would just like to show a video of the agent redrawing the house image. In conclusion, we managed to produce a reinforcement learning approach that can be successfully used in order to teach a machine to draw, without the need for any supervised learning. We showed that the model can recreate images of different complexity and size. This approach also provides a baseline for potential future work. For example, one can extend on this work by teaching the agent to draw specific objects and then combine what it has learned in order to draw more complex objects via skill chaining. Thank you very much for watching the video.